Hello, welcome to the fourth part of my presentation. We will be talking about verifiable computation with SNARKs. So this lecture will be divided into two parts. I will first give a proof of the computation of a recurrence relation, and the later one we will touch on how to do the same thing for any assembly program. So the recurrence relation that we will be using is Fibonacci, which is sort of a tradition in the area of SNARKs, making examples using Fibonacci. We do this modulo a prime number, the number which you see there, which is known as the baby Burr prime. It has the property that p minus 1 has a large factor of 2, right? It has 27 factors of 2, in fact. So the prover will claim that when you apply this recurrence relationship with a0 equals to 1 and some other value for a1, that the element 1023 of this sequence will have the specific value that's there. So, to prove this, the prover, Alice, she needs to construct a trace of the computation with all the intermediate values. So the whole sequence with all the intermediate values needs to be constructed, and this is what we call the trace of the computation. And there are some additional constraints on this trace, on the sequence. The zeroth element has to be 1, the last element has to be the value that's claimed, and the Fibonacci relation should apply, so we need that the a of I plus 2 equals a of I plus 1 plus a of I for all the i's in this interval. Now what we are going to do, which is typical of SNARKs, we will translate this sequence into a polynomial, and we will take these constraints and translate them also into polynomials. So there we go, now we go. The first thing that we need to do, we need to define the polynomial. So pay attention, the y are really the same values of the sequence, but the x's are not simply the interval from 0 till 1023. Instead, we will use some gamma, which is an element in this group of high order, and we will use the powers of gamma as the basis for x. And so we are creating the f of x by interpolating over gamma 0 ai up till gamma to the power 1023 with the y as 1023. So the degree of this polynomial will be 1023, but we extend f over the larger domain. We use a blow-up factor here, which is 8. Now what happens is the following. So the constraint that we had, that a0 equals to 1, will be translated to the following condition. It means that the f of x minus 1 should evaluate to 0 when we substitute x equals to g to the power 0, which is equal to 1. Okay, so this is depicted in this equation. a0 equals 1, which means that x minus 1 divides the polynomial f of x minus 1, and this is saying the same, that if you look at this division, then what you get is a polynomial, right? So let me talk briefly about division of polynomials in case you're not familiar with it. Here we are dividing this 4th-degree polynomial by x minus 7. So the algorithm is quite intuitive. Here we have x to the power 4, so we must multiply x minus 7 to make sure that x to the power 4 appears here. So we multiply it with x3, we do the computation, we subtract, we have eliminated this the degree 4 factor, and now we have a remainder which is of a degree less. So we repeat this algorithm. In this specific case, there is no remainder, so we know that x minus 7 indeed is a factor of this polynomial. The quotient is this column here, so the quotient would be x3 minus 3x2 plus 6x minus 4. And what we are using implicitly is something that you probably know already, right? If z is a 0 of f of x, then x minus z is a factor of f of x, so x minus c is a divisor of f of x. So this is the property that we are using in the previous slide and that we will be using later on as well. So the second constraint, we do something similar. It means that the a of this 1023 minus this value is equal to 0. So the a will be substituted by the f of x, where x is this gamma to the power 1023. So what we obtain is that this condition is equivalent to saying that the polynomial that we obtain, well, the fraction that we obtain by taking the f of x minus this value divided by x minus the gamma of to the power 1023, that this division results in a polynomial. It doesn't result in a rational function, which is the terminology that we use when this division isn't has a remainder which is different from 0. And then the third constraint is quite interesting. So it's this expression that we have here. So let me try to dissect it for you. So the f of gamma to the gamma squared times x corresponds to a of I plus 2 minus a of I plus 1, which is the f of gamma times x, minus the ai, okay? And so this has to be true for all the values from gamma 0 up till gamma 1021. Now, this is, of course, it's a horrendous product, but by some clever trick and choosing the denominator, choosing the value of gamma correctly, this product can be computed fast. Now, we have these three conditions, and so we get these three rational functions P0, P1, and P2, and we want to be convinced that they are indeed polynomials, so that this division is working out well. But instead of using these, evaluating this condition on the three polynomials, we will combine it. We will use a random linear combination of this, which is called the composition polynomial. So what we have is that the verifier will choose random elements gamma 0, gamma 1, and gamma 2. The composition polynomial will be the linear combination of this, and so we believe that if each of these polynomials P0, P1, and P2 are of low degree, then the composition polynomial will also be of low degree. So proving of low degree needs a polynomial commitment scheme. I have explained what the commitment scheme was earlier. And so what we have in this situation is that the prover will commit to the composition polynomial CP. But it's important for the proof to be succinct that this polynomial commitment scheme, it must be compressing. So you can have a huge polynomial of degree 1000 or maybe of 1 million, but the commitment it must be compressing. It's somewhat like a hash function. So the commitment value should be of very, very small size. In this example, the KZG example, the size can be as little as a couple of hundred bits to represent a commitment to the whole to the whole polynomial. Another alternative is called Fry, which uses a Merkle tree. I'm skipping this a bit, but the polynomial commitment scheme also needs to have some other nice properties to accelerate the interactive proof. So what is the high-level sketch of a SNARK? Well, we have that the prover will commit to a polynomial f of 1 based on all the inputs, and it will compute the polynomial, and it will commit the polynomial. Then there will be a challenge. Now, based on the challenge, the prover will compute a new polynomial, commit to it, send it to the verifier, and this go on for maybe 20 steps or so. There is a dependency on these polynomials, which makes that the degree of these polynomials gets smaller every time, and this will convince the verifier that the polynomial indeed has the desired properties. So you may think that being able to create a polynomial for some recurrence relation isn't actually very useful. So to convince you of real applications, we are going to talk about converting any kind of computation into a polynomial. And this process is called arithmetization. And there are many techniques and many variations, but roughly speaking, we can say that there are 3 different ways to model a computation. The first approach is strongly based on R1CS, which is actually it's a sequence of transformation, as I wrote it there, which is based on the first SNARK paper. A second possibility, which was developed later, is to take any Boolean or, as an extension, arithmetic circuit. And a third possibility is to take a list of CPU instructions. So apart from ways to model a computation, there are also different ways of converting a table or a circuit into polynomials. So this leads to a variation of tools, and which are being developed at the time as we are speaking. The issue of these tools are what is the cryptography used, what is their performance, how can we be sure that the software is correct, what is the maturity of the software. For instance, we can have academic software which may not be sufficiently mature for real-world application. So we have all these variations, and so in this context we have now a new profession which is called the zero-knowledge engineer, which is the kind of person who specializes in all these topics. So what I'm going to talk to you about is a ZK-VM, which stands for Zero Knowledge Virtual Machine. And what it does, it takes as an input an assembly program and transforms it into a SNARK for verifiable computation. We also have a ZK-EVM, which is something similar, but it doesn't do it for an assembly program. It does for Ethereum virtual machine code, so Ethereum bytecode. In particular, the ZK-VM that our company is developing is for the MIPS instruction set, so we call our project ZK-MIPS. I'm going to give you a very tiny example. It's very small, and nevertheless you will see how complicated things become. In fact, what I'll be using the Fibonacci example, but instead of using a recursion relation, I have this mock CPU instruction. Essentially, this is just Python, but you can see I have these variables, register 0, register 1, and the operations are quite simple. They are addition, subtraction with 1, and these are just assignments. And what I'm going to do now is I'm going to make a dump, a copy of, or snapshot if you want, of the internal state of all the registers. So I wrote a program in Python to do this, and then the beginning of this is the following table. So this is very, I only have, this is one iteration of the Fibonacci, and I already get like 4 lines of codes. So this is what we call the execution trace, right? So this is an important concept. The execution trace is the whole sequence of computation with all the states of all the registers, and maybe memory, which isn't included here, or the program counter, which also, well, it's implicitly included in the step. So what we are going to do now, we take this this table here, and we are going to create a polynomial for it. So how would we do this? Well, actually, we are going to create a polynomial for each of the registers here. So we have f0 is a polynomial corresponding to r0, f1 corresponding to r1, etc. And now what we are going to do, we are going to, we have listed the opcodes. So each opcode will result in some constraint. So what happens is that in this case, R2 is equal to R0 plus R1. But you must realize that these R0 and R1, they are referring to step 0, the state of step 0. So in polynomial constraints, what we get is that R2 in state 1, in step 1, is translated into the F2 of 1, and then the whole condition will be like this. So F2 of 1 minus F0 of 0 minus F1 of 0 is equal to 0. So what we get is that the opcode will translate into this specific constraint. We should also remember that the other registers, they are not affected, so that we get that we get 3 additional conditions which are on the registers which have not been affected. So just this condition just says that, for instance, that in f0 of 1 minus f0 of 0 equals to 0 is just saying that register 0 is unchanged. Okay, so this is the general idea of how can we create a polynomial from the execution trace. So when you think of a virtual machine, this is what you conceptually what is going on, what you should keep in mind. Now, I didn't say that. We also need to include the initial and the final constraints. I didn't put it here because it would make the table too confusing. But of course we get that the f0 of 0 equals to 1, the f1 of 0 equals to 2, etc. So what does this bring us? Well, a real program can easily have millions of opcodes, right? So this results in polynomial of very high degree, of a degree a couple of million, even a billion. Larger than that, we simply cannot deal with at the moment. So what are the performance parameters? Well, the prover needs time to compute these polynomials. So, and this is very, very intensive. It can take hours to compute. So this is one of the performance parameters. Of course, we need to know what will be the proof size. Proof size can vary from a couple of hundred bytes to, megabytes. But of course, the bigger the proof gets, the less interesting it becomes. And then a third parameter which we must take into account is the verification time. And remember that verification time in case of the zero-knowledge rollups transforms into Ethereum gas cost. I know that the proof of slowdown is at least 6 orders of magnitude, so that's at least a factor of 1,000,000. Probably it's more. There are projects to optimize and to get this lower, but this is one of the challenges that we are facing. There has been an academic project called ZK that actually solves this problem for a very specific language. They defined their own small programming language for which they solve this problem. So as we speak, libraries are being constructed to implement ZK-VMs. And so I want you to give this feeling that it's somewhat like electrical engineering, right? We are working with opcodes and instructions, but the hardware is different. The hardware isn't electrical, isn't chips. The underlying hardware here are polynomials. Well, we know now that zero knowledge actually is an ambiguous term, and in traditional meaning, zero knowledge often isn't used as zero knowledge, but as a way to talk about succinct proofs. Verifiably outsourcing a computation has many applications beyond rollups, so that's just a second importance. A large interest is now about rollups, but I think there are many applications beyond rollups. Cryptographers are in high demand, should be obvious, and it's even expected to become worse. I do expect that the area of multi-party computation and fully homomorphic encryption will grow in the next couple of years. So in the context of fully homomorphic encryption, what you can do is that the user will encrypt his input, send the encrypted input to the cluster, to the cloud. The cloud will perform the computation on the encrypted input, give the encrypted output as a result, and then the user will be able to decrypt the output to get the real output. So for general computation, this is kind of difficult. There's a tremendous slowdown, but in specific contexts, we are already seeing specific primitives which are working. We see efforts specifically in the area of privacy preserving artificial intelligence, privacy preserving machine learning, which accomplishes this. So it means that a user can use an AI model and still preserve his privacy. So this is truly important. I want to call your attention to online course that's going to be presented by me in the next couple of months. It's a high-level introduction to zero knowledge and SNARKs. It covers about the same topics as had been done in this lecture. The intended audience is, say, interested programmers or other professionals with some technical background, but not necessarily with a strong mathematical background or a strong cryptography background. We will catch up with some of the original crypto. And another thing is the focus is on understanding the concepts. It's not to focus on really the mathematical proofs. I will give you references for the people who really love to go through the proofs, but this is more to get a general understanding of this area. And so there will be some hand waving going on in the course. Whoever wants to go through the details, you can find them yourself. And so the idea is to discover things through programming, not through mathematics. And there will be additional exercises based on IPython, the GPython notebook with the Galois extension. So this is what we are presenting to you for over the next couple of months. Please stay tuned. Hope to see you there. Bye-bye.